Okay, welcome to the second day of the Magnesium Battery Conference. The two sessions today were organized by the eMagic project. Thank you very much for this. My name is Daniel Messling. I'm responsible for communication at the Cluster of Excellence Polis. And today I will supervise the technical part. And Luis Colmenares from CEDATEC will moderate the both sessions. Now some short technical announcements. Probably most of you have been there yesterday at the first day of MACBAT. But if you have any questions, you can ask them in the Q&A field on the right side on your screen. And if we have too many questions, the panelists can also answer the question then after the presentation. The event will also be recorded like yesterday, but not all speakers have given their consent, so you will get access to a set of presentations via email, I think, by the end of this week. If you are interested in single presentations, please contact the speaker directly. So we have also a small adjustment to the agenda. Ayan Mukhirji will replace Ran Atyas. And so now I would like to hand over to Luis and Humberto. And enjoy the conference.
Thank you, Daniel, for this introduction. I would like to share my screen now. Yes, as Daniel pointed out, I am Luis Colmenares from CEDATEC Energy Storage. I belong to the management team of the project eMagic. I really like that you today enjoy all the results that during the two sections we will present today. Get into the outcomes from the project eMagic. Also, I would like to thank Keycap and Daniel and colleagues for the chairing this organization of this international symposium. Our session today will have 10 presentations. 5 of them will be by already senior scientists, and 5 of them for our young scientists. Hope that you enjoy all of them. As Daniel pointed out, please, your questions can be written in the Q&A section. Saying that, I would like to introduce Alberto Blasquez, my colleague Alberto Blasquez, who is the coordinator of the project. He will present in details more about the project.
Thanks, Luis, for your kind introduction. First of all, I would like to thank also to the organizers, especially to Maximilian, Daniel, and Christian, for giving us this opportunity to show our activities in the framework of the European eMagic project. I want also to thank to my colleague Luis, because also he has been involved in the organization of this second day. Thanks, Luis, for all your involvement in this organization. Let me start with a brief introduction about my company. CEDATEC Energy Storage is a technological center that is located in the north of Spain, in a very beautiful town, as it San Sebastian. Actually, we are around 75 people working in the field of batteries. Since the beginning, we were founded in 1997. And since the beginning, our main objectives has been bridging the gap between the more fundamental R&D and the industry, trying to giving value to the industry by means of the direct transfer of knowledge in the field of batteries. For two kind of cases, for the improvement of current battery technologies, but also in the development of more disruptive and novel batteries. Currently, we are mainly focused in the development of advanced lithium-ion technology, but also we have some activities in the development of post-lithium-ion technologies, as for example, solid-state batteries, as well as, for example, lithium-sulfur. And in the middle term, also we have some lines oriented in the development of more disruptive technologies, as for example, magnesium-based batteries, but also other battery technologies based on zinc, for example, zinc-air, zinc-iron, or zinc-hybrid batteries. In this slide, you can see the value chains that we cover in the field of batteries, mainly, as I said at the beginning, in the field of lithium-ion. We go from the material to the final application. We have nice and good capabilities for electron manufacturing and slurry processing. Also, we have a pilot plant for battery manufacturing. We are able to manufacture cells with different formats and designs up to 40 ampere hours. And also, we have a strong team in the design and development of module and battery packs for different final applications. Here in the corner, you can see a picture about a successful history of a current commercial electric bus that contain a battery pack that has been developed by CETEC. Okay, in the second part of this presentation, let me show you the MAGIC project. MAGIC project is a European project that has been funded in the framework of the Horizon 2020 program. The project starts at the beginning of 2019 and will finish at the end of 2022. CETEC is leading currently this project and the coordinator of this proposal, where some of the most important research centers around batteries field are on board of this project, as for example, Technium, Maryland University, University of Cambridge, Denmark Technical University, CA, KIT, DLR, and CSIC in Spain also. Also, we have the luck to have one company on board, as it is Abengoa, that guarantee that we will be able to demonstrate and analyze the feasibility of magnesium batteries at the end of the project. This is a picture of the kickoff meeting of the project in January of the previous year. I would like to thank to all the consortium for their involvement in this community. I hope that you will enjoy during today the technical results that are coming out from the project. Starting with the motivation of this project, let me say some remarks. A part of the technical point of this disruptive technology is clear. Yesterday, several colleagues demonstrate that this disruptive technology could suppose a very good alternative to the current commercial batteries. But and yesterday, for example, Marcel Weil comment about the risk of the supply chain of this magnesium element due to the fact that the most of the production is located in only few countries around the world. But thanks to the abundance of this element in the earth, as well as the good distribution in practically all the regions around the world, it's a guarantee that this will not be a problem in the future. Other important point about magnesium batteries in general is that the strong and old magnesium industry guarantee a good recycling rate of this element in all the cases. It's well known that this element could be recycled actually in the different fields with a successful recycling rate of more than 25%. That is much bigger than the, for example, lithium element. Okay. The main objective of this MAGIC project is the development of two different magnesium-based batteries technologies, magnesium ion and magnesium sulfur. The idea is to find and develop new disruptive approaches that will demonstrate the feasibility of this technology. This is, let me say, the technical objective. But we also have in this consortium another and also important objective, that is the build a strong community around this field that guarantee go faster in the demonstration of the feasibility of this technology in a short period of time. I will start with the technical part, with the technical objectives. This slide presents the overall approach of the project. We are divided in different work packages, from the development of high reversible anodes and good electrolytes with higher electrochemical window, as well as two kind of different cathode materials, integration materials from one side. Also, we are evaluating organic integration materials to develop feasible magnesium ion batteries. And also, we have a more challenging approach based on the development of magnesium-sulfur batteries. All of this always taking into account that all the approaches that we are going to validate in the framework of this project should be at the same time validated in real cell prototypes in order to assure this feasibility that I said before. In this table, I'm not going to go in deep in details of the target that we have in this project, but as we will see in the next presentation during this session, we will see that it's important since the beginning, taking into account that all the developments that should be done by the scientific community need to have into account that some important parameters or key parameters in order to understand from the industry if the approaches that we are developing are feasible or not. Just some examples, as for example, the loading of the electrodes. We can see a lot of approaches in the literature, very good approaches, but where the electrodes have a very low loading, that is difficult to evaluate or calibrate the impact of these approaches. Also, the amount of the electrolyte normally is huge. The economic efficiency normally are very low. And what we try in the framework of this project is not only to go ahead in the finding of novel approaches under fundamental point of view, but also try to identify which are the key points in this technology in order to assure the feasibility of this technology. More or less, this slide represents what I said before, that this is the normal way that different battery technologies have proceeded during the last years. This is the case, for example, of lithium-sulfur. Just to put just one example, we can find in the literature different approaches that show thousands of cycles, but when you try to make a real full-scale prototypes, you need to add a very huge amount of electrolytes. The energy density of the final system is very low, and probably some of the approaches that are described in the literature should or need some feedback from the industry in order to focus or put attention in the most important part of the technology. That's to say, summarizing, this is the approach that we follow in the MAGIC project. Since the beginning, we are developing the technology in parallel. We have two important lines. The first one is try to find new or novel solutions to overcome the current limitation of the technology, and always in collaboration with a strong team that is working in evaluate these approaches in real cell prototypes in order to assure the feasibility of this technology. As we will see in one presentation this afternoon, the different components of the cells are very, very important. But we estimate that at the end of the project, if we are able to develop novel cathode materials with higher voltage or higher specific capacity, as well as electrolytes with higher or wide electrochemical window, we estimate that it will be able to achieve cells with at least 150 watt-hour per kilogram that demonstrate the technology. Apart of the technical objectives, another important objective, as I said before, is create a community, a strong community around this field. We believe that it's very important to evaluate synergies between different partners in order to assure go faster in the development of this technology. We have different plans, but we are open for the collaboration with other centers around the world. If you believe that you can help us or you can find synergies with our consortium, please, you can get in touch with us by means of our webpage, also by Twitter, or if you prefer, directly by email to email address, mine or the address of Luis Colmenares. Just to finish, let me summarize the breakthroughs that we fixed in this project. The first one that I think that we have achieved already is established tools for modeling and simulation that allow us to go faster in the identification and development of new materials of electrolytes. In fact, in the next presentation, Jan Goswit from DTU will present the results that we have got in the framework of this project. Also, the idea of this project is try to analyze and develop practical and very thin reversible magnesium anodes, because in the literature, most of the people use magnesium anodes with very huge thickness, 100 or more. And the idea is try to develop magnesium anodes with around 20 or even less microns of thickness. All of this work will be presented by our colleague, Doron Arbach, from the Bar-Ilan University. The next presentation will be presented by Senju. He will show the advances in the development of new and novel high-capacity anode-like magnesium cathodes. My colleague Ineko from CIETEC will represent the improvement that we have made during the first 18 months of the project in terms of manufacturing and scaling up of the cell components. But also we have another target, as for example, analyze the feasibility of these technologies by means of the life cycle assessment of LCC assessment also. Another important point is reinforce during the next month the community that we have created in the framework of IMAGIC by means of international collaborations, dissemination activities, as for example this international symposium, as well as education of young scientific in the field in order to guarantee that we will have a strong community for the development of the technology. Just to finish, let me show you some figures that we have got in the first 18 months of the project. By the moment we have published in the full consortium around 12 articles. You can find all this information in our webpage. Also, we have made around 10 contributions to international conference. We have established computational tools for material design and identification and validation. And we have established the first basis for the scaling up of the cell components in order to demonstrate the feasibility of the technology. And at the end, as I will show in one presentation, we have achieved or we have developed a postal with 200 milliampere hour of capacity that in principle is able to give around 15 watt-hour per kilogram. Okay, just to finish also, I would like to thank again to the MAGIC Consortium. I would like to thank to all the people that is joining this session, and to participate, and I hope, I expect that you will enjoy this session. Okay, Luis, if you have any comment or...
No, thank you, Alberto, for the nice introduction about the IMAGIC project. As you pointed out, now we will start to learn some of the outputs that our colleagues in the consortium have achieved. We will start with our colleague Pior from DTU. He will present some outcome from the modeling for the materials selection. Please, Pior, the board is yours. Thank you.
Thank you very much, Luis. So I'm postdoc at Technical University of Denmark, and the role of DTU is to provide the computational support for the development of magnesium batteries. So I will present the overview of our activity that we did during this month. So I'm going to skip the introduction to magnesium batteries because we heard a lot about this already. But at DTU, we are focused on development of materials for all three parts of the batteries. And we can set some goals to all of these materials. But in general, when we think about batteries, the new batteries, we want them to be safe, to have a high capacity, and to provide a high difference in the voltage. So if you are thinking about the calculations, we can help in the development of materials in two ways, by doing calculation for many different materials and try to screen and propose some new materials, or trying to provide some understanding and explanation of the properties that we have already seen, and then go to more rational design of the materials. So during the presentation, I'm going to show you 4 examples of the support from the calculations on the cathode side, electrolyte side, and also if you are interested in anode, please stay to the talk of Smolny Vincent, that is a PhD student at DTU, and is working on the anode side. So starting with the cathode, our main task is to provide some materials to say which materials should have the best properties for being the cathodes in the magnesium batteries. And to do that, we are going to study hundreds of materials, and that's a lot. So to do that manually, to do calculation manually, is quite complicated. And to do that, our colleagues here, Felix and Ivano, already established the autonomous procedure for calculating, and it minimizes the interaction of human with a computer. So basically, it's some kind of script, some kind of program that do everything instead of us. The human interaction is just we need to prepare inputs, so list of the materials that we want to screen, and then make decision a few steps. So at the beginning, the script is calculating the stability of the material. Then we calculate the potential, electrochemical potential of the material. And at the last step, we are calculating the properties about diffusion. So as we can see, we are going from the properties that are very easy to calculate to more advanced. And thanks to that, at each of the decision steps, we can decide if some of the materials already don't have a properties that we want, so we can just keep them and do the more advanced calculation only to the materials that are the most promising. And thanks to that, we are saving computational time, and we can see more materials. So the most important in that is that we are looking both at thermodynamics and kinetics. And in case of magnesium batteries, it's very important because magnesium very often gets stuck in the structure. So we can have a material that will have a very high potential, but then we cannot remove magnesium at all. So this cathode doesn't work. So if you will do entire procedure, at the end, we will have properties like volume change, stability of material, and also potential and energetic barrier at different states of the charge of the batteries. And based on that, we can say which material should behave good in experiments. So we already did the studies, the screening for over the 100 structures from ICSD database. And based on that, we were able to indicate some new materials that can be promising. And our studies indicated these 2 materials with quite good properties, with high potential. Maybe energetic barrier is a bit still high, but for other one, we have a bit lower potential, but very, very low energetic barrier. And indeed, these materials were an input to our experimental partner in Barcelona, the group of Professor Rosa Palazzini, where this material were already synthesized, and they are undergoing the experimental tests now. Moving to another part of the work that we are doing on cathodes is valentetta sulfide. And here you already heard about this material yesterday, because we are collaborating here with KIT. So Jenny was presenting experimental results yesterday and showed that this material has very specific electronic structure. We see the bonding, anti-bonding orbitals here from S22- ligands that are, this structure is completely collapsing when we add in more electrons. And also the flexibility of the structure provides a very good diffusion path. Okay, so you can see that thanks to the structure, the energetic barrier is lower. You can see that, okay, the energetic barrier is still high for this case, but we are doing calculation just for one magnesium in the structure. So if you want to see what really is happening in the material, we need to look what is happening when we are charging completely material. So we were doing this, just putting magnesium atoms in random places, trying to find the most optimal place where magnesium will sit. And we are doing this for many random configuration to find out which structure will be the most stable. And here I'm presenting the structures that got the lowest energy. And what is interesting here is that if you look, when we put extra magnesium to the structure, it always goes to the place close to magnesium already. So the magnesium is not uniformly located in the entire cell. It's always just close to each other. And then if we look at the energies, so I should mention here that each of the dots, green and blue dot, represent one structure and one energy that we got. So in fact, we are interested just in the lowest energies, so the lowest dots. So if we look closely into that, we can see that for the structure with magnesium, from 1 magnesium to 5 magnesium in the structure, we have energies that are indicating not stability of the phase. That means we have a phase that has, for example, 3 magnesium in the structure, which will decompose, disproportionate to the empty one, and the one with 6 magnesium. That means this material have a very specific charging mechanism that at the beginning is heterogeneous, and then when we reach the phase that is stable, we are able to charge it homogeneously, so charging 1 magnesium by 1. So because of that, when we look at simulated OCV, we should have a plateau and then potential that is slowly dropping. And indeed, if you compare that with the experimental results from KIT for the first cycle, we can see that at the beginning we are seeing plateau and then it's decreasing. So we did calculation up to concentration equal 1. So if you see here, we have a quite good agreement for the potential that is close to 1, and here is 1. But what is interesting is what is happening here. So this is still undergoing because it's a very difficult region of the cathode, and you are trying to find what is the structure there, how it does it impact the kinetics, and what is the degradation mechanism, because we can see that after going here, the cathode behaves completely different way. And so far, what we see in the calculations is that the bond between vanadium and sulfur is very weak when there is a lot of magnesium close by. So probably we will observe the formation of MGS inside the cathode, and probably this is the degradation mechanism that is causing the completely change of the shape of the curve. So switching now to electrolytes, so far the requirements for the electrolytes are that electrolytes should be readily stable with a metallic anode, so to prevent any formation of passivation film that could prevent the ionic transport between electrolyte and magnesium. So because of that, we are using usually low polar solvent, and that together with double charge of cation causes huge aggregation of the system and formation of clusters. And indeed, these clusters are responsible for most of the properties of electrolyte. So if we want to study the change of the solvent or salt and look how is the impact on the electrolyte properties, we need to find out what is the structure of these complexes. So indeed, in DTU, we are trying also to suggest some other solvent or change of the salt. So at the beginning, with going to the solvent, we did just simple screening, just looking at interaction energy in the vacuum between magnesium and different solvents, different group of solvents. And what we noticed is that from the solvent that we screen, only ethers providing like middle strength of the interaction. So only these solvents will provide easier desolvation. So we went in more details into the limes. And here, first, we noticed that in the community, usually it's used, community usually uses THF or monoglyme because the solvents are quite simple, creating simple structures that you can easily determine even if XRD. They give a high dynamic, low viscosity, but the problem with them is that they have also high volatility because the boiling point is quite low. So that means if your battery will start to heat up, there could be a very dangerous situation. So what we wanted to do is to switch to some other glymes, longer glymes, extend the chain, and thanks to that we can avoid the low boiling point, so have lower volatility. But the problem here is that the structure is quite complicated of the complexes and the desolvation mechanisms also. But we wanted to study this. What we want to do to see how the change of the solvent will impact the electrolyte performance. So for that, we just took the simplest system as we can imagine. So just chlorine atom, chlorine anion, and this system we have a simple anion. It's the most common system, and a calculation for that can represent many different types of the electrolyte. And inside this electrolyte, electroactive species are created by the reaction between these reagents. And as a result, we are usually getting monomagnesium clusters like that, or some more complicated multimagnesium clusters. So to understand everything, we need to look both at the formation of monomagnesium and multimagnesium clusters. So going to monomagnesium clusters is quite easy. These clusters are quite simple. To study them, to find out what is the structure, we just need to look at the energies when we add more oxygen atoms close to the magnesium, and then observe when we will see the minimum energy that represents the most thermodynamically stable state. So we can do it for many different solvents and for many different structures with one chlorine and two chlorines. And we can see that for most of them, the coordination number 6 is preferred, but for longer lines, suddenly also 7 is a little more stable. That can be quite surprising because magnesium would expect that it always will be coordination number 6 or maybe even lower. But indeed, when you look at the literature, there are already some reports about the coordination number 7 for magnesium. This is for magnesium TFSI in tetraglyme, when magnesium is coordinated by the 5 oxygens from the tetraglyme and then 2 anions. And that's just because of the super strong chelating effect of these glymes. So then we wanted to go also to more advanced systems, so with multimagnesium. And these multimagnesium clusters can be seen as a result of reaction of the simple clusters together with MgCl2 with a salt, and creating the dimers, so clusters with 2 magnesium or even 3. We could go also further, but DFT calculation is getting very, very expensive if we include much more magnesium. So we have to stop here. But what we can say here is that if you go further, even here we have a lot of topologies, how the atoms are arranged, and that we need to test all of the examples to know which one is really the one that's providing the lowest energy. So for example, if we look at this Mg2Cl3, we have a 3-2 possibility. One is the pyramidal, when you have 2 magnesium here and here, and 3 chlorines that are shared between this magnesium. And also it can be like we have a linear one, when with 1 chlorine that is shared between 2 magnesium and 2 chlorines that are just separated onto 1 magnesium. And if we just do the calculation trying to put there also solvent, solvating the magnesium, we can see that the lowest energy structure we get for THF only if we consider these pyramidal structures, because THF has a more bulky structure, so it prefers that magnesium will be coordinated also from a lot of chlorines. If you look at the glymes, they have a more halide system characteristics. So it's they want to make some kind of disk around magnesium, and that limits access to the magnesium from chlorine, and that's why they are preparing a linear one. But what's interesting here, if you look at DIGLime is behaving quite different. It's also like creating linear structures, but they are more condensed and going more into direction of this more aggregated. So we can do that for all of the clusters. And here I'm showing just the summary of this analysis. So showing only the most stable structures that we found in a schematic way. So the energies are showing the formation energy calculated per one magnesium. And what is important here, I should mention at the beginning, is that when you want to compare the energies between clusters that have a single charge and double charge, we need to, so we have a release of chlorine, and this chlorine is usually reacting in the electron with another component, like here, for example, LaCl3, and that reaction also needs to be included if we decide if some cluster is more stable or less stable. So for LaCl3, the energy the correction that needs to be included is around 26 kilojoule per mole, and for others, we estimate it's like 20-30 kilojoules per mole. So if you look at this, only for monobline, the differences are very, very small, and double charge cluster will be stabilized like this. What's other interesting, if we are comparing tetraglime with triglime, we can see that the structures are very similar. These two solvents are almost providing almost the same clusters. So the fifth oxygen from the tetraglime is just stabilizing the cluster, but doesn't really change the nature of the solvent. Also, what we can see is that there is huge similarity between monoglyme and triglyme. So usually the structure is like, if you take two monoglymes, it represents one triglyme. Only diglyme is behaving quite different, because if you can see here, for example, the one diglyme is shared between two magnesiums that makes them much closer and the structure much more condensed. And here, even the structure is really aggregated because of that. So what's happening here? Diglyme has just 3 oxygens, and this apparently is too little for fully solvate magnesium, but it's too much to use 2 molecules of diglyme just to solvate. The solvatation shell will be too crowded if you are using 2 molecules. So the system is just evolving to more concentrated systems, to more concentrated clusters, creating things like that. But the most important is to see what is the connection between these structures that we generated, that we think they are most stable for the electrode process. And as the electrode, we have 2 processes that are happening. And so we have desolvation and reduction. These 2 processes are overlapping on each other, but in calculations, it's very difficult to make it like in the same time. We can do calculation for desolvation, just removing magnesium, and also doing the calculation for reduction, adding 1 electron to the system. And when you compare these results with the clusters that we created, we see that increase in cluster size have a positive impact on desolvation, because it's easier to remove magnesium when there is also another magnesium in the structure, but it has a bad impact on the reduction. The good impact was found if we have chlorine that are bridging in the structure, so they are connecting 2 magnesiums, because in that case, the electron density that is shared from chlorine to both magnesium can be easily shifted from one to another in case of we remove 1 magnesium or we reduce one of the magnesiums. And a high solvent content is also positive, have positive effect on the desolvation, because if you have more content of solvent, it's the interaction between magnesium and chlorine are getting weaker. So because of that, it's much easier to remove it. So based on that, we can see why THF is working so good, because it induces the best clusters that we can see. But if you want to go to some other solvent that is less volatile, big lime is just the best candidate among the limes. I have also the fourth part of the presentation, but I can see that I don't have time. Luis?
Yes, a couple of minutes more. Go ahead.
Okay. So we are also trying to find some new anions, because we know that chlorine are not good because they are causing corrosion of the battery. So we want to find some anions. So in the project, we are using this salt that we developed in KIT, and we just want to see why this salt works so good. So first of all, we went through the literature, just studying different anions salts that were reported to provide a good plating stripping, calculate for them the interaction energy. We see that for boron 1, it's really the interaction energy is quite small, but also for others, like the interaction energy can be higher, and it's possible to plate. So it's not the most important. We were trying also to look at the stability, calculating electron affinity and ionization potential, calculating this also for TFSI, that we know that it really doesn't work, TFSI, so to try to see the difference. We also relax the structure, calculate reduction potential, oxidation potential, but we cannot see anything like indicating. So we went through many different descriptors that can find us. And finally, we found that the bond dissociation energy in the reduced form of this cluster can serve as a very good indicator if the salt will provide us reversible plating stripping. So you can see for all of them, you have a positive value, and only for TFSI, there is negative value. And why this descriptor works? Probably because when we reduce magnesium, we are going through, and we want to plate, we are going through this metastable magnesium plus state. And we want, of course, to reduce it more, add more electrons. But what can happen is just this super reactive species will react with anion, and we will see the decomposition product. So what we want to stop that. So we need to design the anions in the way that they will provide the stability against this electron. So what we try to do is just to look at this anion and see if we put other ligands there, what will happen. So we did calculation for reduction potential, oxidation potential, and also for dissociation for the first anion and second anion. And based on that, we can select some ligands that should be promising just based on that, with a high oxidation and low dissociation energy. And then going to the decomposition, we found out that this mechanism of breaking this bond and this bond is the weakest point of the salt when we add this magnesium plus. So we studied this for all of the ligands and find out that there is quite clear connection between the structure and the stability, because if we have a lot of groups connected here to this carbon, it will stabilize the radical formed here. And if we have a lot of like withdrawing groups like CF3, we will have stabilization of this species. And all of these effects are just moving the reaction in this way, making it easier to break the structure. So we need to, when we design an ion, we need to find the balance between this withdrawing of the electrons due to that we want to have low dissociation energy, and this not too high withdrawing because we will lower the stability. So if we look at the structure selected on the previous slide, and with the one that here with calculation are showing that we have a stability, we can see these three, and indeed this is the one that is extensively studied in our project. So here I have a conclusion to each of the parts. I think I don't have time. So I just hope I managed to show you that DFT calculation can be really useful for development of battery materials, both by screening this and or providing some understanding of already seen results. And at the end, I just want to thank all of the group of BTU who is working on eMagic, and also two experimental groups that we are collaborating the most in the eMagic project. And thank you.
Thank you, Pierre, for this nice talk. So far, I don't have any Q&A here written from the audience. Let's see, probably one, John Sebastian Filo, who is thank you for the nice presentation. Actually, it's a very useful tool that you over there are developing at DTO in cooperation with the other partner, KIT, on the IC map in Barcelona. So here now come the question. Thank you, Jan Sebastian. Just one question remains. Is why considering reduction in the double layer and not at the surface?
I mean, we cannot see that, we don't do calculation for the surface. So it's just, everything is just in the solventation.
Okay, I think we run out of time. You had, I think, one question more in the Q&A, a couple more in the Q&A from Stuart Robertson. So Pierre, please go ahead and test the reply to him, because we are already running out the time. Thank you, Pierre, again for your nice presentation. Let's move on to our colleague from KIT, Chen-Yu Lee, who will talk about high capacity on long life and magnesium storage cathodes. Please, Chen-Yu, looking forward to your contribution. Thanks.
Yeah, thank you, Luis, for the introduction. And hello, everyone. My name is Chen-Yu Lee from KIT. And our contribution, or our main task in the eMagic project, we are dealing with the cathode. So we are aiming at high capacity and long cycle life magnesium cathode. And we are also involved in the development of the magnesium electrolyte. But we are mainly focused on this chlorine-free electrolyte system. And that's why today I just want to show you our kind of compatibility test of the non-corrosive electrolyte with different magnesium cathode materials. So to start my talk, I would like to give a brief introduction of the development of magnesium electrolyte. And I think some of the points has already been given by Professor Aubach in the previous talk. So basically, if we change from the lithium system to the magnesium system, if both cases we use the metallic anode, we will face definitely different issues. For example, when we the electrolyte that has been used in the lithium batteries, the carbonate, for example, it's not compatible with magnesium anode. So in case of lithium, we always have like the ion conductive layer on the lithium surface that kind of protect the lithium anode, so that we could have continuous cycling. But in case of magnesium, the reaction between magnesium and the solvent will result in a passivation layer that's blocking further ion mobility. Also, another point I want to give in is that there will be a native oxide layer on magnesium surface. So we need some kind of activation so that we have fresh magnesium towards the electrolyte. So our goal is to achieve this reversible plating and stripping of magnesium. And I mean, the first generation of magnesium battery that could deal with this problem or realize the reversible magnesium stripping and plating is to apply a Grignard-based electrolyte. We know that Grignard agent is reactive, and they could conditioning the moistures and also some oxidant species in the electrolyte solution, and could also somehow clean the magnesium surface. And with the addition of the chlorine species, we have the well-known APC electrolyte reported by Professor Aubach's group. And definitely with the addition of chlorine, we have an extended like electrochemical window, and we also have better ionic conductivity. But the limit is still like in the APC case, we have a relatively narrow electrochemical window. And this kind of limit us to further develop the high, or just to investigate the magnesium storage in a high voltage cathode. Also, the nucleophilic nature of the electrolytes makes it incompatible with sulfur cathode and also with the organic cathode. And that's why several non-nucleophilic electrolyte has been developed. For example, the magnesium TFSI with the magnesium chloride case, as highlighted by Professor Aubach, and also the magnesium HMDS electrolyte. This is also in combination with the mantanic chloride. So in this case, we could see that from the CV, we have like extended oxidation stability for up to 3.5 volts, which is much improved than the APC case. And also, as demonstrated in the magnesium sulfur cell, it's compatible with the electrophilic cathode materials. So, in fact, with this non-electrophilic electrolyte, we already investigate the magnesium storage capability in a broad range of cathode materials, but then there's still the remaining issue, the chlorine. So we know that there are, the chlorine has multifunctions in the system, but the corrosion is still like the issue there. So this is especially the case for oxide, for example, the transition metal oxide, which is still the choice of the market, I would say, in the case of lithium-ion batteries. And also, it's a promising high voltage cathode material for magnesium batteries. So you have to somehow find a way to develop an electrolyte that is also at least compatible with this high voltage cathode. Also, the chlorine or the corrosive issue makes us to think about, at least we have to make special design, anti-corrosive design in the cell manufacturing, for example. This is will add additional cost and efforts. And on the other hand, we also have a complicated solution environment with dynamic equilibrium in the chlorine-based electrolyte. As shown before, we have a couple of this magnesium chloride cluster species, and this monocharge carrier has a possibility even to intercalate into the system as a whole rather than the double charge carrier. And as reported before, the magnesium chloride storage, if we have this scenario, then we might need more electrolytes if we want to achieve the same specific capacity as in case of this magnesium ion storage. So there's an urgent need to develop a chlorine-free simple salt electrolyte. And we also work in this direction and develop the electrolyte of such kind. And here is the structure of this this electrolyte. So basically, we have a large anion, and which contains a boron center and this fluorinated alcohol ligand, and this makes a weak coordination between the anion and the cations, and also this means we have better dissociation and higher ionic conductivity in the electrolyte solution. So from the CV, we see we have even higher oxidation stability of up to 4.5 volts against platinum. And we have very efficient magnesium stripping and plating as shown in the reduction and oxidation peaks. So the long-term cycling is also good. In the symmetric cell, we could run it for more than 1,000 cycles, and we didn't observe like obvious increase of this plating stripping over potentials. So with a nice electrolyte solution, we move one step forward. So we checking the compatibility between the electrolyte with different cathodes, just to check whether it is just as we expected. The first electrode or the cathode we tried is the benchmark cathode, the Shepherd phase. And what I want to mention here is the combination between the Shepherd phase with a chloride-free electrolyte system is not straightforward because as reported previously, the chlorine ion has the, let's say, a decisive role on this charge transfer at the interface of both the anode side and also the cathode side. So we know that the chlorine ion has a strong affinity to the magnesium, and this will, of course, change the coordination environment of magnesium in a solution. Also, that tends to form the adsorption layer, as Doron mentioned before. So this is kind of protecting the magnesium so that we could, on the one hand, have an efficient plating and stripping, and also ensures a prolonged cycle life. And at the cathode side, we also, the chlorine has could reduce the activation energy for magnesium insertion by changing the solvation, and also the Shepherd phase, the surface molybdenum atoms has certain catalytic effect for this dissociation between magnesium and chlorine. So this further improves the insertion kinetics. And so there's no doubt that the combination between the Shepherd phase with chlorine-based electrolyte is successful, but the multifunction of chlorine also makes it difficult if we want to replace it with the chlorine-free electrolyte system. And but the case is that we tried it, and the compatibility between our borate electrolyte and the Shepherd phase is quite good. So as shown in the charge and discharge curve here, we have a nice plateau and also a good capacity and low overpotentials after the first few cycles. The initial low capacity is related to the activation process at the magnesium side. So we also observed the similar phenomenon or activation process in the magnesium symmetric cell by using this borate electrolyte. And here, just to in order to deal with this problem, we also try to introduce additive amount of magnesium borohydride to the system, just hoping that it could somehow clean the magnesium surface. And the cell indeed shows a good capacity and also distinct plateaus, voltage plateaus, even in the first cycle and onwards. So this means it works. Also, the long-term cycling at different current grades, we see that the cell could be cycled for more than 300 cycles, and this also means that magnesium boron hydride with trace amount of this magnesium borohydride will not affect on the long-term cycling, and this is also something I want to mention. So with the kind of successful compatibility test, we also tried with another cathode which has a higher capacity and also has a higher voltage. So here I want to present it like this Polymer Castle, the polyanthraquinone structure. So basically the charge storage mechanism of this pack material relies on the redox of these carbonyl groups. And if we consider both carbonyl groups involved in the reaction, we have a theoretic capacity of 260. But in the practical case, as reported previously, the accessible capacity is only around 110, so which is only like less than half of the theoretic value. On the other hand, we also noticed that they have used the graphite as the current collector. The reason is quite simple. Graphite is more anti-corrosive than the normal aluminum foil. So we also did a comparison study by using the chlorine-based electrolyte coupled with this packed cathode, but we have used this carbon-coated aluminum as a current collector. As shown here, the cell could only be charged and discharged for a couple of cycles and then ends up with very long overcharging, which indicates some corrosion happening. So the corrosion can be somehow mitigated by using a chlorine-free electrolyte system, but we also noticed that the low capacity might be from the cathode formulation. So because we know that in principle the polymer material has a relatively low conductivity, and if with the normal preparation method we could only have very limited accessibility of this active material from the anode. That's why here we have used a reprecipitate method, and that we're hoping to have homogeneous loading of the active material on a carbon matrix which has a high surface area, so that we could have increased the conductivity of the cathodes and also have more contact with electrolytes. So we hope by this approach we could increase the capacity as well. So here I show you some typical electronic microscopy images, and basically we see that so the first column is the pure carbon matrix, while the second column is the carbon with the active material loading. So we see the amorphous region, which was marked by these original orange colors. They are like dispersed well on the carbon matrix. So then we tested the battery performance using this new cathode design and also coupled with the borrowed electrolytes. And here we see basically we could run a cell for up to 500 cycles with the normal or let's say standard cell components, which indicate a good compatibility. Also, here we could achieve high capacity with the new cathode formulation, and this is close or even exceed the theoretic capacity a bit. And with the homogeneous distribution of the active material on the conductive carbon, we could also achieve fast kinetics, as demonstrated here in the CV with different scan rates. So the next material I want to show you is the vanadium tetrasulfide, which I have presented yesterday. So I don't go to too much detail here. I only just want to highlight is that previously there's also a report about this VS4 cathode, but they could only achieve a capacity of let's say less than 150 milliampere hour per gram, and this is still with less than 1 electron transfer per VS4 structure. But if we switched to this borate electrolyte, we have much improved capacity, and also we have a very nice platoons. And the reason, or a possible reason, could be that the sulfur dimer we have in this PS4 structure, they are quite sensitive to the nucleophilic species. So if it's coupled with the APC electrolyte, then we have the breaking of the sulfur-sulfur bond, so that, of course, we have a relatively lower capacity. And the last example is, or the compatibility test is with the high capacity sulfur cathode. So in this section, we have investigated the sulfur redox by using this borate electrolyte, and we use the operando Raman technology, and also to relate the Raman modes with different polysulfide species with the help of DFT calculation, and this result in these two graphs. So basically, we have the change of different polysulfide, or let's say polysulfide species evolution during charge and discharge process. And in principle, we have like a reversible conversion from elemental sulfur through this long chain and short chain polysulfide intermediate species, and ends up with the magnesium sulfur at lower voltages. And so this reaction mechanism is quite similar as what we have investigated before by using the chlorine-based electrolyte. So this also means that our electrolyte is compatible with the sulfur cathode. To sum up, I would say that the chlorine-based electrolytes are still prevalent electrolyte for magnesium batteries. So the fact is that the chlorine has multifunctions in the magnesium, or let's say enable magnesium plating and also insertion, de-insertion. Now it's still difficult to find, or there's no report about some additives that can replace the chlorine ions. But we should also realize that the corrosion issue is really the big problem, especially if we want to scale up the system, and in the manufacturing, for example, this will bring or a lot of problem and needs more efforts. As reported yesterday or presented yesterday by Justin, they are trying to find out some alternatives for this chlorine species, but from our side, we believe that the chlorine-free electrolyte system is a more straightforward solution, and is practically more feasible for this processing and manufacturing, which makes the easy transfer of the knowledge or the technology. Also, the sample sort system offers more possibility to just to tune the electrolyte solution without much concern about this complex equilibrium. This is very important for the sulfur battery and also for the organic battery, I think. We know that even in case of lithium-sulfur battery, we have to rely heavily on the additive, this lithium nitrate. But in case of magnesium-sulfur system, we are still looking for a proper additive that could at least extend or prolong the cycling with the sulfur cathode. But I mean, the chlorine-free, the sample salt electrolyte system is definitely a good benchmark. So from where we could further develop or just to tune the electrolytic property and its compatibility with different cathode materials. As I have presented today, the magnesium borate electrolyte has good electrolytic properties and can be applied to various cathode systems. In the next step, we are trying to just to check the compatibility or the magnesium insertion to high voltage cathode materials because the advantage of the electrolyte system is also like they could provide a large electrochemical window. And also we are persuading a high energy system. Also, we hope that the long-term cyclic stability in the symmetric cell could also be transferred to this full cell system in the future, hopefully. And then at last, I would like to acknowledge the financial source, especially from eMagic project and also from this Polis and Maximar. And also the slides, we have the main contributors from Jung Zhaokager and also Vinaya and Yanlei, and also the firmness and support from Krishna. And with that, I would like to thank you for your attention.
Thank you for your nice talk and contribution. Just one question. Afterward, you can follow the another question by the Q&A chat. Yeah, if you want to reply. Just one question having here from Nekjung Dan Singh. They say, thank you for the nice talk. Why do some no chloride DME based electrolyte has anodic stability, probably far above anodic stability of the solvent like DME? For example, 4.5 volts versus magnesium for a magnesium borate electrolyte in DME.
This is a good question. I think this is also like the research topic, or the presentation what has been shown yesterday. So where they did this.
This is because of absorption phenomena.
Sorry?
So this is because of absorption phenomena. You have absorption phenomena that extend the electrochemical window. It's a metastability which is reached by absorption phenomena. It relates to the absorption of the anion on the electrode.
Yeah. And also, I think there will be some kind of some layer formation on the anode side, or some let's say in case of the lithium-ion batteries, we also have this problem, but in that case we have some oxidation of this aluminum foil, where we could have like extended operating window, electrochemical window. Yeah.
So thank you. Please look at the question that you have in the chat, in the Q&A chat. Just follow your reply to the attendance. Thank you. Let's introduce the next speaker. Our colleague Eneko Asaceta. He will present a stepwise process to manufacture and validate magnesium battery cells. Please, Eneko, the floor is yours.
Great. Thank you, Luis, for your introduction. Let me share the screen. Can you hear me, and can you see the screen?
Yes, perfectly. Just go ahead.
Okay. Thank you. The talk I'm going to give today is entitled Stepwise Process to Manufacture and Validate a Magnesium Battery Cell. And I'm going to start the talk. Just one. The talk by refreshing the MAGIC project's objectives, well mentioned by my colleague Alberto in his talk, and explain why we choose them. For that, I will use an example, what we learned from other technologies, and how we came up to the MAGIC project's strategy. Then I will compare the coin cell and pouch cell as development tools, and I will give some results on pouch cells and the optimization we are doing at CDTech. Finally, these results will help us in designing a roadmap for the following 2 years of the MAGIC project. As my colleague Alberto mentioned this morning, a MAGIC project owns 3 objectives. The first one is to create an European community around magnesium batteries. capable of developing a magnesium battery, but also capable of validating it. Why these objectives? If we have a look on the development timeline of lithium-sulfur, for example, we can observe that there was paid a big effort on material developments at lab scale for a very long time. And it was not until relatively recently the pouch cell device was ignored, let's say. And consequently, the development timeline took two steps. The first one was an intensive work at lab scale, but it was missing the lack of prototype perspective and application perspective. Then, when they arrived to prototype level, they realized, it was concluded that not every lab scale approach was valid in real prototypes, and consequently, the technology validation or demonstration is taking time. In the MAGIC project, then we are proposing another strategy, which is the simultaneous development at lab scale and prototype scale the technology. In this way, we aim to shorten the development timeline of magnesium. It's true that coin cell level device is a very powerful tool, and it serves to show the proof of concept for magnesium ion batteries. Based on this system, we all know it, a pure magnesium anode, usually 100 micrometers, an APC-based electrolyte based on Grignard reagents, an intercalation cathode made of several phases, molybdenum sulfide, and in this system, yes, the plating stripping of magnesium was demonstrated. Also, the intercalation of magnesium in several phases, and also certain reversibility at coin cell level. That's why this system has been named as reference magnesium ion battery system for a very, very, very long time. Coin cell is also valid not only to demonstrate the concept, but also to evaluate different components like separators, electrolytes, different magnesium-based anodes, cathode formulation, and cathode loadings. As an example, I give some figures in this slide. However, coin cell does not give us other relevant information, and for that is needed pouch cell system. Like, for example, in coin cell level, the balance of the cell is usually ignored. The excess of magnesium anode can reach 1000% at coin cell level, where the objective is to reduce it as much as possible in real prototypes. With the electrolyte volume, it's similar, and at coin cell level, we can reach very high values, above 100 microliters per milliampere hour. And to demonstrate the technology, we need to reduce it as much as possible. As a reference, 4 microliters per milliampere hour is given in lithium-ion batteries. When we start developing pouch cell devices, we can start analyzing the contribution of each element into energy density. And in this way, we can identify the limiting components and optimize them. And in this way, we can somehow forecast or estimate the potential of the technology. At CDTech, we started with pouch cell development by using pilot plant cathodes provided by one of the partners of the project, and stacking we designed a relatively small pouch cell composed of by 4 electrodes, double-side coated, the corresponding anode separators and stacking them together. The first approach to pouch cell was transferring the conditions of coin cell level to pouch cell level. That is to say, keeping the cathode loading usually used at coin cell level, 3.5 milligrams per square centimeter, a fixed separator based on glass fiber, high volume of electrolyte, and relatively thick anode foil, up to 100 micrometers. This pouch cell delivered 40 milliampere hour per gram and was reversible for certain cycles. This pouch cell delivered 4 watt-hour per kilogram energy density, which is not a very competitive value. But the interesting thing when analyzing the component contribution to the pouch cell mass, we realized that the active material, the material giving the capacity, cathode coating, represented only 10% of the whole system. This is not realistic in a real device. And, well, we came up with the conclusion that coin cell system cannot be extrapolated to pouch cell level, and we need to optimize, to redesign the system at pouch cell. Consequently, sorry, the slide is not. Okay. Consequently, the following pouch cells integrated cathodes with higher loading, and the separator was replaced by thinner alternative. Sorry. This pouch cell was giving around 40-45 milliampere hour per gram and delivered 15 watt-hour per kilogram. This is not a competitive value, but we start. It's a good starting point because the contribution of the key components, which is the cathode, represents a higher percentage of the whole cell. Also, analyzing the contribution of other elements or components of the cell, we realize that there is room for improvement. On the one hand, we can improve the several phase loading in the cathode to improve the energy density. Then, well, the current collector is nickel in this case, but if we are able to replace the electrolyte but a non-corrosive alternative, and in the frame of the project, some partners are working on it, we will be able to replace it by aluminum, and consequently improving the energy density around 5%. Then, if we are capable of reaching or delivering higher values of capacity, up to 70 milliampere hour per gram, which is a reasonable value at coin cell level, we will raise the energy density to around 40 watt-hour per kilogram. These values are, well, not very competitive, this is true, and consequently we came up with the conclusion that several phase is a good reference system, and it allows us to take the first steps to pouch cell manufacturing. However, this material is not competitive in terms of energy storage, energy density, and that's why we need new materials. In the project, in the MAGIC project, there is a big effort is being paid to identify and develop high performance materials, and these are some examples of them. If we estimate the energy density we will reach using a couple of examples of these materials, we could reach, in this case, values above 100 watt-hours per kilogram, which is a good value to start to validate the technology. Back to several phase and analyzing the effect of other systems or components, sorry, like the electrolyte. Coin cell, well, it's not a good system for studying the amount of electrolyte because there is a minimum amount of electrolyte to fill the internal space. Consequently, the volume capacity ratio is not realistic in a real prototype. This high amount of electrolyte hides the detrimental mechanism in the cell, and consequently, we have overrated cycle life. That's why the effect of the electrolyte must be studied at pouch cell level. In the lower part of the slide, we estimate the effect of the volume capacity ratio if we could be able to diminish this parameter to values close to the ones used in lithium-ion battery. We can boost the capacity, the energy density of the pouch cell up to 25%, which is a significant value. Similarly, magnesium anode at coin cell level is used in thick foils, like 100 micrometers. If we go to pouch cell, these values represent, for a cathode of 12.5 milligrams per centimeter, this loading represents an excess above 1,000%. Obviously, the cell is not well balanced, and to promote the energy density, we need to reduce this excess to reasonable values, around 50 or 100%. In practical dimensions, for this cathode, this loading, it needs to be below 20 micrometers. Fortunately, well, if we raise the loading, this value will also be higher and easier to be processed, which is the limitation of magnesium anode, the processing. Working in this field, some of the partners within the project are working on it. The validation of the technology is not compresses not only the scientific or technical aspects. It is also needed to carry out the environmental impact analysis. Once we start analyzing the contribution of each element in the composition of the pouch cell, we can start thinking what is the energy and material consumption to manufacture it, and therefore calculate perform the LCA analysis. In this field, other partners in the MAGIC project are working on it. As a summary, in this slide, I would like to represent which is the improvement of the energy density when we are optimizing each element of the pouch cell. And thanks to it, we can establish the activities and the research lines to perform it, and the partners of the MAGIC project are facing these limitations. In conclusion, in the MAGIC project, there are two simultaneous research lines. The first one at coin cell level to identify and develop new materials and solutions for the technology, and the most promising approaches will be transferred to our 15 watt-hour per kilogram reference pouch cell, we will integrate these approaches and start optimizing the cell to reach values they can allow us validating the technology. And in this way, we justify the strategy of the MAGIC project. This is the last message. I will thank for your attention. I would like to thank also the partners of the MAGIC project, and I will be happy to answer your questions if you have.
Thank you, Nico, for your nice talk. I think we don't have so far. I didn't see any questions in the chat. Anyhow, you had any questions, please write it down in the chat, and Nico will happy to reply. I really thank you that now with the Nico presentations, we finished our first sections of the workshop today. As you can see, how in the MAGIC consortium we move from the modeling, computational development, computational tools, validation, also kind of the output, on how also all together we try to integrate all new developments inside fundamental understanding into try to make a real pouch cell prototype, which is not no straightforward issue. That's why we are this consortium to deal with that, make a real rechargeable magnesium battery. With that, I will like to announce that we will have now a break. The break will shorten to 10 minutes. I apologize for that because now we are 5 minutes ahead of the schedule. That means that we will come back quarter after 4. Andrews. She will present us her result related to the continuous modeling of transport and interface phenomena in magnesium electrolytes. Please, Janina, the board is yours.
Okay, thank you for this kind introduction. So as announced, I will give you an overview about continual modeling of transport and interface phenomena in magnesium electrolytes. And thereby, I will focus on 2 different electrolyte systems about which we already heard a lot today. So the first one is this state-of-the-art chlorine-free magnesium borate electrolyte. And the second one is the combination of magnesium T+I and magnesium chloride in DME. So let's start with the first magnesium borate electrolyte. From experiments, it is known that the cell voltage of symmetric magnesium cells increases with the electrolyte concentration. So this is in contrast to the results of our first simulation. So we would expect that a higher concentration will lead to faster kinetics at the electrodes, and this would result in a decrease of the overpotential with the electrolyte concentration. So obviously, this is not the case, so the big question is why. It is known that magnesium salts are prone to form ion pairs or bigger clusters, and furthermore, we know that the solubility limit of this magnesium borate salt is quite low at around 0.5 mol per liter. So with this electrolyte concentrations that are used in experiments, we are very close to the solubility limit. And therefore, it seems likely that something like pre-nucleation clusters are formed in the electrolyte, which then affects the battery performance. So that's the motivation to have a closer look on the ion agglomeration in this magnesium borate electrolyte. So as a first step, we had a closer look at the equilibrium between the dissociated ions and neutral clusters. And during the ion agglomeration, solvent molecules are released from the formation shell of the magnesium cation. And this leads to an increase in entropy, which is assumed to be the main driving force for these cluster formations. So when we now have a look at the law of mass action and the mass conservation, we get this formula which relates the amount of free magnesium, say this here, to the electrolyte concentration. And since magnesium is a spiral and cation, which means that there are strong electrostatic interactions, and we want to have a look at high electrolyte concentration, we can't assume that our electrolyte behaves ideal. So for the activity coefficients, we therefore use the David equation to describe this non-ideality of this magnesium cation and the following anion. Since the exact properties of the clusters are not known yet, we looked at the influence of the equilibrium constant K and the cluster size Z on this equilibrium. And in general, we see that there is a critical concentration, which you can see here as a maximum in this graph, at which this cluster formation takes place. And thereby, the cluster size has only very small impact, whereby the equilibrium constant K more significantly influences this critical concentration. But although we analyzed a wide range of values for K and Z, the critical concentration is always here in this range, which is exactly the range that the experiment has a look at. The next step is to include the clusters into our transport model. And I only will give you a very short summary about this newly developed model. And if you're interested in more details, you can find them in our recent publication. So as I told you, the non-ideality effects may play an important role in magnesium electrolytes, and therefore we consistently included the non-ideality via the effective chemical potential. And then the cluster formation equilibrium, which I showed you in the last slide, gives us a relation between the electrolyte concentration and the concentration of the dissociated ions, the cluster, and the amount of free solvent. For the conductivity and the transference number, we use the experimental data from our partner KIT, and the diffusion coefficient is described as a function of the cluster concentration. And finally, we use the Vassar-Form approach to describe the kinetics at the interface, and thereby we assume that the plating from the clusters is in principle possible, but kinetically unfavorable. Moreover, the solid anion is very bulky, and therefore it may skillfully hinder the plating reaction, which we also consider in our model. So with this model, we have now done a parameter study and looked at different values for Z and K, as well as the electrolyte concentration and the current density. So here you can see the results for 0.4 molar electrolyte at the lower current density, and we found that more stable clusters lead to a higher overpotential. And this expected behavior is more pronounced for smaller clusters. Moreover, we can see that when the clusters are thermodynamically unstable, then larger clusters are more unfavorable for the battery performance. And the opposite is true for stable clusters. So here in this case, the larger clusters are more favorable for the overpotential. So when we now compare the influence of Z on and K on the cell voltage, which can be seen here as well, and this the influence of K and Z on the concentration of free magnesium, we can see that there seems to be an inverse correlation. And that's the reason why we have a closer look at the relation between the cell voltage and the amount of free magnesium. So these two graphs show the results for the two different current densities, and each data point in this graph represents one K and Z combination at a certain electrolyte concentration. By including and excluding the different effects of the cluster in our model, it was possible to explain the different features of this graph. So the first eye-catching feature is that there are some fluctuations here, and this is caused by the influence of the cluster size on the electron transfer kinetics. Moreover, we see that there's a maximum of the overpotential And the reason therefore is that we included the non-ideality into our model. Additional feature can be found at a high current density. So this pronounced solar field can be assigned to transport limitations in the electrolyte. But all in all, we can say that over a wide range at both current densities, we observe that the overpotential decreases when the amount of free magnesium increases. So this implies that the main effect of the clusters is that they reduce the concentration of our main electrochemically active species. So from experiments, we also know that the overpotential for a 0.3 and 0.4 molar electrolyte is almost similar at low current density, and this can be used to estimate value pairs for K and Z. And with that, we find that the equilibrium constant exponentially decreases with the cluster size. So consequently, bigger clusters need to be less stable to have the same effect on the overpotential. More interestingly is that the clusters seem to be thermodynamically unstable and independent of their size. So now that we know value pairs for K and Z, we can come back to this comparison between the experiment and the theory. So without considering any clusters in our model, we weren't able to reproduce the experimentally observed concentration dependence. But when we now include the ion agglomeration and use the determined K and Z values, we can qualitatively reproduce this experimental data. So consequently, the clusters are key to explain the measurements from our partner. And now that we know value pairs for K and Z, we are also able to identify the ideal electrolyte concentration. So here you can see the cell voltage in dependence of the electrolyte concentration for 6 different K and Z value pairs and 2 different current densities. And thereby this minimum indicates the ideal electrolyte concentration where we have the smallest overpotential. And as you see, the cluster size has only a very small influence of this ideal concentration, which is always somewhere between 0.3 and 0.4 mole per liter. And thereby the ideal concentration slightly decreases for battery operation at a higher current density. Interestingly is that this ideal electrolyte concentration is reached when the cluster concentration in the electrolyte is about 0.01 mole per liter, which is not a lot. So we can say that the adverse effect of the clusters becomes relevant as soon as possible. So let's now have a look at a different kind of electrolyte which contains chloride. So as you already heard, it is known that the magnesium cations form various different smaller and bigger clusters with chloride anions, and that although the chloride-containing electrolytes are corrosive, they are often used because this clustering with the chloride anions seems to be beneficial for the dissolution, and therefore it facilitates the cycling reaction. And with our continuum model, we hope to get more insights in the role of the chloride in the electrolyte and at the interface. So, for example, one question is, which of all those possible species is the main electroactive species? So, as you already heard earlier, our colleagues from DTU also had a closer look at all those different magnesium chloride clusters, and they determined the free energy for each of them. And these results from the DFT calculation are the basis for us to have a closer look at the thermodynamic equilibrium between those clusters and the bulk electrolyte. So what we do is we minimize the total energy of the system, and thereby we apply mass conservation as a constraint. And we also consider the non-ideality effect. And as you can see here, we included lots of different magnesium chloride species in our calculation. So, for example, we also considered partially solvated and unsolvated species because at non-dilute solutions for non-dilute concentrations, they could become favorable due to entropy effects. So usually our partners use magnesium P6I, magnesium chloride in a ratio of 1:2. So that's the reason why we had a look at this electrolyte composition. And here on the left, you can see the relative amount of DME, which can be found in which species. And here on the right, you can see the same for magnesium. And as this color coding is quite complex, I highlighted the relevant species. So we see that at very small electrolyte concentrations, the magnesium salts are fully dissociated. But then when we get to more practical concentrations, the solvated magnesium chloride plus becomes the dominating species in the electrolyte. When then the electrolyte concentration further increases, the neutral solvated magnesium chloride and the solvated magnesium K+I ion pair become thermodynamically favorable. And when we then have a look at even higher concentrations, we see the formation of bigger clusters, especially of this magnesium 3 chloride 4 cluster. And our colleagues from Bailan University were able to isolate these clusters as a crystal by drying the electrolyte. So this is quite consistent with our results. So to sum up, that ion agglomeration is to explain the experimental data of this magnesium borate electrolyte, and thereby the clustering takes place as soon as the critical concentration is reached. And furthermore, these clusters are unfavorable for the battery performance, and with our simulations, we were able to determine the ideal electrolyte concentration. Moreover, we started to analyze chloride-containing electrolytes, and we found that the most stable species in the bulk electrolyte at practical concentrations is the solvated magnesium chloride plus. So with now knowing which are the main species of electrolyte, this will be the basis to have a further look at the kinetics at the electrode and to adapt our formula for magnesium kinetics to the chloride-containing electrolyte. And so we hope that with partners we can have more information about the role of the chloride in this magnesium battery. So thank you for your attention, and now I will answer your question.
Thank you, Janina, for your nice presentations. Dealing to a better understanding of the development of this electrolyte. Actually, it's good how you, from the computation tool that you are developing, help us to optimize electrolyte, understand better the relationship with the battery performance on electrode activity. So far, I don't have any QA question here posted. Anyhow, if somebody want to know more about the work performed by Janina, please get in touch with her through the QA chat, or look at the recently published paper that she had on this topic on the coming ones related to that issue. Yes, anyone, Janina, take care if there's any question pop up during the next 10 minutes, okay? In the QA chat. Thank you again. I think that we will now to introduce the student from the German Aerospace Center, Joachim Hecker. He will present some insight of the polysulfide dissolution behavior on line-based electrolytes. Please, Joachim, the board is yours. I'm looking forward for your presentation.
So, thanks, Louis, for the introduction. Good presentation. And thanks for the organizers for the for having this conference and to share or to give me the opportunity to share my latest results with you. My name is Joachim Hecker. I'm a PhD student at DLR in Stuttgart. And after my colleague Janina had a modeling perspective on magnesium batteries, I now want to give you some insight into the polysulfide dissolution behavior in lime-based electrolytes for magnesium-sulfur batteries. My talk is outlined with a short motivation in the beginning, and then the main method of operando UV spectroscopy and microscopy. And with this method, I want to show you some insights into the dissolution behavior during cycling and OCV, and to conclude with the influence of the electrolyte solvent in the end. We heard a lot about the magnesium metal and its benefits, but why magnesium-sulfur batteries in particular? Magnesium-sulfur batteries offer a higher volumetric energy density compared to lithium-sulfur system. In contrast, the gravimetric energy density is a bit lower, but still way higher than current lithium-ion technology. Normally on this introduction slide, you can read about magnesium dendrites are not present in this system, but I think this is not the case. There are a lot of literature showing that classical dendrite formation is not present due to a higher surface diffusion. But indeed, 3D magnesium growth using the separator as a scaffold, practical current density is still observed. And you can see on the right side a recent publication at practical current densities. There's this spherical growth, which might be tuned by electrolyte and separator adjustments. So this issue might be overcome in the future. Overall, magnesium and sulfur are naturally abundant, cheap, and non-toxic, which makes this system promising system for large-scale application, maybe, as Professor Fichtner mentioned, also for stationary energy storage. Why operando UV spectroscopy? To study this system. We haven't heard much about the sulfur system in this conference, so I want to give you a short, the basics of the sulfur system. It's comparable to lithium sulfur, so it relies on the reduction of sulfur to magnesium sulfide in the cathode, and it's accompanied with the polysulfide shuttle, which is the origin for the fast capacity decay and the restricted cycle life in all sulfur batteries. And the benefit of those intermediate polysulfides is that they absorb light in the visible and ultraviolet spectrum. And this makes it possible to detect those species. You can see in the bottom part those absorbance, the wavelength is quite distinct, so you can distinguish between each species. Here you can see the spectra of some, or the spectra at selected stages during cycling of a magnesium sulfur cell. And those peaks are assigned to sulfur species according to previous literature. Which is quite interesting here is that this S4 species is quite dominant during discharge, while it was not chemically accessible by Beaker and other groups. So this might be only formed electrochemically during the cell, but still the stated fact that climes do not stabilize and S4 might not be true. Those wavelengths marked here or in bold are those wavelengths I focus on, and those species assigned to it. Here you can see the voltage profile in the top part of a magnesium sulfur cell cycled at C/20, and in the bottom part the corresponding response or from the UV spectra, and on the right side the operando microscopy picture. And you might see now during discharge there is a coloration of the separator, and during discharge it vanishes again. So you see the separator coloration. Towards the end of the discharge it vanishes, starts again to color, and then towards the end of the discharge it's decolored again completely. You can also see a black coloration around the magnesium ring or at the edge, which might be electrolyte decomposition or some sulfur precipitation, polysulfide forming magnesium sulfide at the anode surface. To have a closer look at this behavior, I selected some stages here. You can see in the beginning there's already a high initial concentration of S8 and SH2- after cell assembly. In contrast, the long or short chain polysulfides are not present. So MgS4 and MgS6 are not present, not that dominant. They are formed during the first discharge plateau, and you can also see that they cause this strong yellow coloration in the separator. Towards the end of the discharge, all sulfur species, or the concentration of all sulfur species declines, and the separator is decolored again. This is quite reversible, so it's observed in every cycle. Having a look on the subsequent charge, the reoxidation takes place of all sulfur species simultaneously, but it's incomplete. So you find short chain polysulfides, MgS4, MgS6, even at the end of the charge at a quite high charge cutoff potential at 3.5 volts. In fact, no S3 radical was observed. This is in agreement with the former studies by Beaker done 2 years ago, something like that. One can argue that with the lower C rate, it's possible to achieve this complete reoxidation, which is in fact true. So you can see here that at the end of the charge at point F, the separator is decolored again. But this also triggers the polysulfide shuttle. So the polysulfides have elongated time for diffusion, which is not beneficial in the subsequent discharge. So you have detrimental effects on the anodes, which might not be too beneficial. Fast C rates, in contrast, increase the over potential and also reduce the capacity gain. So you see here quite a significant influence. If we have a look on the self-discharge, so the behavior during OCV, severe self-discharge is observed in all glymes we examined, with a high initial elemental sulfur and SA2- concentration. And after around 20 hours, the short chain polysulfides take over, so they are formed at the anode side and are then dominant in the electrolyte solution. If you have a look on the first plateau in the subsequent discharge, this is completely missing. So MgS4 formation is already took place, and no capacity can be gained from that. In the subsequent cycling, the concentration of the short chain polysulfide is rather stable at a high level, while the elemental sulfur concentration declines. So there's all polysulfides present in the electrolyte. Now I want to give you an insight into the influence of the electrolyte solvent. We examined the 3 different glymes: monoglyme, diglyme, and tetraglyme. We see the chemical and physical properties in the bottom table, and the first 3 cycles on the right side. If you have a look on the charge behavior, the overpotential rises with longer climb length, which is due to an increased overpotential, increased solvation of the magnesium cation, which is despite the fact that tetraglyme exhibits a quite low donor number or lower donor number than monoglyme, for example. But it's due to the chelate effect. So there's a strong solvation of the magnesium cations in this case, and this causes this overpotential desolvation at the anode. And also the capacity gain is reduced during charge. This is also obvious in the subsequent discharge. that the capacity of the first plateau is shortened, or is reduced. In contrast, the solvent influence on the discharge potential plateau itself, so the position, is neglectable after wetting. And when we have a look on the third cycle, you can see that monoclime already shows overpotential during discharge, indicating cell dry-out. So might not be the solvent of choice for long-term cycling in practical cells. To have a deeper insight, we synthesized some solutions and investigate the conductivity and viscosity. You have here the pure solvent, the solvent with polysulfide solution, then the electrolyte solution, and the electrolyte with the polysulfide solution. And you can see that the conductivity decreases with climb length, which is for the same reason I mentioned before. So the stronger solvation of the cations with longer climbs. So tetraclimb increases the solvation of the magnesium cation and reduces their mobility. So conductivity decreases. In contrast, viscosity increases, which is following the same trend of the pure solvents. So this is mainly determined by the solvent itself. The influence of the polysulfides are neglectable, at least in this concentration range. So this is a quite low concentration of 10 millimolar, but higher concentrated polysulfides are not synthesizable yet. But I think it's comparable to practical cells, so I think this might not be an issue to consider at the moment. And based on this insights, decline offers the best compromise, as Piotr already mentioned before. It offers a moderate magnesium solvation, so the desolvation energy is lower than compared to tetraclimb. The volatility is lower due to the higher boiling point, and the viscosity is still quite low. But still, also with the decline, we observe this polysulfide shuttle and the self-discharge. So it's not perfect, but from this climb family, I would recommend to use this one. With this, I want to conclude operando UV spectroscopy and microscopy are well-suited methods, and with this to study the polysulfide dissolution behavior. And with this method, we found that even directly after cell assembly, there is a high initial elemental sulfur concentration in the cell. And during discharge, MgS6 and MgS4 are formed, and they decrease, their concentration decreases again towards the end of the discharge. During charge, an incomplete reoxidation is observed, even despite the high charge cut potential. Slow C rates are beneficial for this complete reoxidation, but only for the short chain polysulfide. So the long chain polysulfides are still present and cause or involved in this polysulfide shuttle. Severe self-discharge was observed in all glimes, unfortunately, with the dissolution of S8 in the beginning and the subsequent formation of shorter polysulfides. And from the glyme family, decline is recommended due to a best compromise of solvation, viscosity, and volatility. With that, I want to give a short outlook, because we only had a look on this mechanical intrusion cathode, so this was simply mixing elemental sulfur and carbon. But there are a lot of other polysulfide retention approaches promising from the lithium-sulfur system. For example, to access those narrow pores, you need the vapor phase infiltration method. In addition, there's also host surface functionalization, covalently bound sulfur or polar additives to be considered, and we are already in collaboration with partners to investigate those. With that, I want to thank the EU and the Federal Ministry for Education and Research for funding eMagic and Maximal, those two projects. And I want to thank all the partners for this already nice collaboration, and my students for all their lab work done. And thank you for listening.
Thank you very much.
Thank you very much for the nice presentation, the new approach to learn more about the electrolyte, inside of the electrolyte on the effect of the solvent. Sorry. I had one question here about recently from Murat Gebgetse. He said the discharge of voltage is 0. Is this useful for the magnesium sulfur cells? This seems to be a large usable window from application point of view without the risk of over discharging. Thank you very much.
Yeah, in fact, that's not a practical voltage range. So I mentioned before, 3.5 volts during charge is quite high, and also 0 volts during discharge is quite low. But we want to examine the edges where those species are reduced or completely reoxidized. So we want to stretch this this window a bit, and this gives insight for further cut-off voltages. So in fact, the cathode has to be improved, so the O potentials have to be minimized. That's true, but also to elongate or to widen this window to investigate where those species are reduced or oxidized gives hint for further definition of the cutoff potentials. Hope this answers the question.
Yes, otherwise he will again write down in the Q8. We have one more question. We have time for that question as well. Sorry if I don't pronounce correctly the names, but it's from Brashark Akisetti. He say, hi Joaquin, nice talk. How come the magnesium sulfur has high theoretical energy density than the lithium sulfur system in terms of gravimetrics?
The gravimetric energy density is lower, or what was the volumetric?
Yeah,
the gravimetric is lower. So the volumetric energy density comes from the high volumetric capacity of magnesium. But in contrast, the gravimetric is lower than.
Yeah, probably I'm misreading during the presentations from her side. Yeah.
I can go back to the beginning. See here.
Yeah, probably. Yeah.
Gravimetric is lower.
Yeah, exactly. Yeah.
Mm-hmm. Hello, Joaquin. Luis, we have time for another question.
Yes, we have 1 minute more, at least a couple of minutes.
Okay. I have a question regarding that. Today we have seen several presentations with a real great improvements in magnesium ion technology with good new intercalation materials, as for example, vanadium sulfide, polyanthraquinone, and so on. Materials with large specific capacity and also good discharge voltage. How do you consider, taking into account the result that you have shown, the competitiveness of magnesium sulfur technology in comparison with magnesium ion? In lithium is clear, but in the case of magnesium, I'm taking into account the low practical voltage of such technology. Can you give us your opinion?
Yeah, indeed, the O potentials are quite high at the moment, and there is definitely room to improve. This is one thing I mentioned in the last slide. We want to examine some redox mediators together with VTU to access the second plateau where the most of the capacity is gained from, which is which is opening, I would say, the field for high energy density cells. But yeah, there's a lot of work to be done, and at the moment the magnesium ion cathodes look more promising, especially when you have a look on the recycling performance. So the capacity decay is also quite severe in magnesium sulfur.
Thank you very much, Joaquin.
You're welcome.
So let's thank again to the speaker, Joaquin. Thank you very much, Joaquin, for your great job on work. Let's move to the next speaker, our PhD student from DTU, from Technical University of Denmark, Smovin Vincent. He will present his work related with the computational design of magnesium alloys as anode for magnesium battery. Looking forward, Smovin, for your presentation.
Hope that, can you see my presentation now?
I think you need to change the display setting. Just click on the display setting and put in the presentation. Over there in the menu bar, in the display settings, Smovin.
So is it perfect? Is it perfect now?
No.
How about now? Does it work?
No, I think you need to change your settings. In the display setting, you switch to the presentation mode.
I changed it.
No.
Is it fine now? Oh.
There are three menus on the top of your screen. In the middle, you see display settings. Can you click on that?
Yeah, I changed actually.
Oh, the menu doesn't open. There's a little triangle next to the display settings. Can you click on that?
I tried it.
Now it's
okay.
Great.
Okay.
Yes. Thank you, Maximilian.
Yeah, sorry for the delay. So thank you, Luis, for your kind introduction. And thank you, the organizers, for giving me the opportunity to share my results here. So as Piotr in his talk indicated, I will be going to talk about magnesium alloy anode in magnesium batteries, specifically ductile magnesium alloy anodes. So I'm a PhD student at Denmark Technical University. And the motivation, so as you can see, so the formation of the passivation layer is one of the well-known problem in magnesium batteries. So when the magnesium metal anode come in contact with conventional electrolyte, it always creates a problem of formation of a passivation layer, which is impermeable to the magnesium ions. And there is two solutions actually to bypass this problem. The first solution is using intercalation or conversion type anodes. So basically the normal intercalation anodes use the bismuth, antimony, tin, or indium. But the problem with using this type of anode is one of the biggest problems is the volume change associated with this type of anode. As well as the other thing is that in order to exploit the energy density of a magnesium battery, we should use magnesium metal in its elemental form. Then only we can completely exploit the magnesium battery in terms of energy density. So the other solution is to use improved electrolytes. So that means like the APC or MAC electrolytes. Then we can use magnesium metal. But then the problem is like the magnesium has low ductility. So due to the external crystal system of magnesium is inherently brittle. So then the solution comes is we have to use a ductile magnesium alloy anode. So when I say it's ductile magnesium alloy anode, it refers to a low dopant concentration. So the dopant concentration we added should be very low. Then only we can, as I say, we can completely exploit it in terms of energy density. So my work is basically on ab initio density functional theory investigation, which I made in search of ductile magnesium alloy anode. So the workflow is as follows. So the main aim of the work was to obtain a ductile magnesium alloy anode, and its electrochemical behavior should be similar or closer to pure magnesium. And the first step, we were screening the dopant, so the alloy. So first we were looking whether the dopants we added improve the ductility. Then we checked whether for that we actually started with 33 dopants which already known to improve the ductility from the previous studies. Then we checked whether these dopants whether these alloys are stable. After checking whether these alloys are stable, then we checked the electrochemical behavior of the magnesium alloy. So the alloy, the chemical behavior of the magnesium alloy should be closer to the pure magnesium. And for that, the first thing we have to study on the ductility. And here, what you see here, the main reason of the ductility is due to the insufficient number of planes for the deformation. So here what you see are the different slip system available in the HCP magnesium, and for magnesium at room temperature only basal slip systems are available. But in order to accommodate the strain along C axis, we need to activate the C+A slip system. And several studies indicate that the stocking fault in the structure can nucleate the C+A dislocation, which in turn activate the C+A slip system. So here what we are looking for, we are looking for the dopants which reduce the stocking fault energy on doping with the magnesium. So we compare the stocking fault energy of the pure magnesium with the stocking fault energy of the magnesium with the dopant, and we check whether the dopant reduces stocking fault energy. And when I say the stocking fault energy, there are mainly three types of stocking fault in magnesium, but the I1 intensity stocking fault is related to the ductility. So the I1 intensity stocking fault means it have a stocking sequence of AB, 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 AB. Then there is an missing of B plane, then it comes AC, AC, AC stocking sequence. And the work of Stanlop et al. Shows that this intrinsic stocking fault have correlated to the ductility of the magnesium material. And the stocking fault energy normally calculated in ab initio or DFT calculations using this equation. So basically the first equation indicates the energy of the structure with an stocking fault, and other one, this EHCP is the normal HCP system, and divided by the area of the stocking fault. But to computationally calculate the stocking fault energy, the energy of the stocking fault structure, it's computationally very expensive because we have to calculate the stocking fault structure. And since we are evaluating the 33 dopants, in this work we used axial nest nearest neighbor Ising model. So in which each stacking sequences are represented with some spin number Si, Sin, and a interaction parameter is defined between them. Then this results in the stocking fault energy as like so. Then it results in 2 times E DHCP minus EHCP. So here we can get the stocking fault energy just in terms of two bulk structures, so which is the HCP structure with AB, AB, AB stacking sequence, and a DHCP structure with AB, AC stacking sequence. And then we evaluated whether this doping give beneficial, did it reduce the stocking fault, so we evaluated based on this term, and the results are shown in this figure. So based on our calculation, you can see most of the elements have reduction in stocking fault. So that means these elements reduce the stocking faults and in turn improve the ductility of the magnesium. And we see like around like 5 or 6 elements which increase the stocking fault energy. So normally these 33 elements we studied known to be like make the element ductile, magnesium ductile, but we expect like this discrepancy may be come from the low doping concentration we used in the study. So the doping concentration we used is 2.98% at 8% of dopant we used in our studies. So we think this discrepancy may come from the doping concentration. And the next step to check whether the alloy is stable. So this is calculated based on the energy of formation with the dopant in the bulk, and it is calculated using this equation. The first term indicates the energy of structure with the dopant. So this is the first figure. So we calculate energy of the structure with the dopant, and the energy of structure without a dopant, and Ex is the energy of the dopant, like the just energy of the dopant in its ground state, and Emg is the energy per atom of the pure magnesium, and thus we obtain the bulk energy of formation. And to a material to an alloy to be stable, the bulk energy of formation should be negative. So you can see the results in this figure. And so the elements which which show a negative elements are like they are mostly stable. So almost 20 elements are stable if you look in, and most of them are rare earths. And the elements which are not stable are mainly first and second group elements which have a bigger atomic radius. This may be the reason that they are not soluble. And the other elements like hafnium, titanium, and zirconium, these elements are known to be less soluble. So this agrees with our study. And the final thing is we want to know the electrochemical behavior of this dopant. So this we evaluated based on where the dopant goes. So we want to know whether the dopant will go to the surface. So if the dopant goes to the surface, then there's a chance of the dopant to be react with the electrolyte, so which may affect the electrochemical performance of the battery. So that's why we don't want the electrode to be at the surface. But we want the electrode should be in the bulk. So this is a 2D schematic diagram. So when you have the dopant in the bulk, then we have a interface, the electrode interface. We have a dopant free surface. The electrode surface is dopant free. So this surface is similar to the pure magnesium. So the dopant didn't have any role in the electrochemical behavior. So now we are going to analyze whether the dopant going to prefer to be in bulk or dopant prefer to be at surface. What we wanted dopants to be in the bulk. And for that, first we analyzed which all are the surfaces present in the magnesium at equilibrium condition. We used the Wolf analysis to obtain the equilibrium shape of the crystal. And we considered almost 12 surfaces in the magnesium and calculated its surface energy. And we constructed the Wolf plot. And from the Wolf plot, it is clear that only 3 surfaces will be possible or present in magnesium at equilibrium conditions. So it's 001 and 10 minus 10 and 10 minus 11 surfaces. And you can see the area fraction of each surfaces here. So then we further studied on these surfaces, whether the dopant prefer to go to the surface or in the bulk. So this study was carried out using these structures. So when I say it goes to the bulk, there is 2 possibilities. It can be in the bulk or it can be in the stacking fold. So even the dopant prefer to be in the stacking fold, then it's like it's in the bulk. So what we want to avoid, we don't want these structures to be favorable. So these are the, so in the DFT calculation, we normally put a vacuum to mimic the surfaces. And we put 2 dopants on each of the surfaces. And then we calculate the energy of formation of all the structures. So the energy of formation with the dopant either in bulk or in stacking fold or in any of the surfaces, so using this equation. And this is a similar equation which used for the stable analysis. Then we compare based on these 2 equations. So these 2 equations are made from the formation energies. And this is delta E bulk means it should be like it's the energy of formation when the dopant is the bulk minus energy of the formation when the dopant in any of the surfaces. And for the stacking fold, so it's like the energy of formation in the stacking fold or energy of formation in the surface. So what we want any of these should be negative so that our dopant will stay inside the bulk. And when we studied the stable, so these are the elements, the 20 dopant which are known to be stable after our second criteria. And we observed like aluminum and most of the rare earths show promising results. So they show to be stay in the bulk. So these elements are favorable to stay in the bulk. That means we get a dopant-free surface when we alloy with these dopants. And to the summary, in my work, I assessed the effect of dopants in magnesium alloy to use as a ductile magnesium alloy based on 3 criteria. The first criteria to check whether it is ductile. So for the ductility, I checked based on the reduction in the stocking fault energy of magnesium. Then I look for the stability of these alloys. So for stable, it should be negative. The bulk energy of formation should be negative. And we identified out of the 33 elements we studied, 20 elements are stable with magnesium to form alloy. Then we studied the electrochemical behavior. So when I say the electrochemical behavior, we look whether we can obtain a dopant-free surface for these alloys. So after evaluating based on these criteria, we got almost 11 dopants which show promising results. Out of that, like, aluminum is only the non-rare, the rest of the elements are rare. And among these identified elements, so based on these identified elements, we also see a commercial alloy which is already available. So this is WE45 alloy, so which are this yttrium and neodymium and zirconium. So these elements are shown to be promising. The only element not in our list is zirconium. The zirconium was not in our list because zirconium was not soluble in magnesium. But several studies indicate that zirconium is soluble when it's added with the rare earths. So we definitely recommend this commercial alloy which can be tested to be used at ductile Mg alloy anode. And this is a preliminary work for the alloy designing. So basically, if you want for the multi-component designing and everything, so this can be a starting point for the multi-component designing of the ductile magnesium alloy anode. And thanks for hearing me. Then I would like to thank my team at DTU, our group at DTU, as well as the eMagic for funding my project. Thank you.
Thank you.
Thank you, Smovin, for the nice talk, actually guiding us to look at alternative anodes, especially these alloys. We are looking forward for your manuscript, your publication on the topic, and also looking forward for the experimental work that we are performing currently in our consortium dealing with the magnesium alloy anodes as an alternative. So far, I don't have any question in the QA chat.
I would have one.
Yes, please, Maximilian, go ahead.
Do we know anything about the fate of these alloying elements that you showed? I mean, if you have this WE45 alloy that you have shown, there are some elements inside. What would happen in a battery when you strip and plate from such an alloy? What happens to these elements?
Actually, I didn't check whether the phases of this commercial alloy. But when I tried to study for this, the dopant just binder alloys. So what we really wanted, we want the phases to be HCP or like stain HCP. So that's like right now, like people are studying the alloy with like AZ31 kind of alloys with aluminium. So actually, I really want to see see whether which are the phases. So I actually didn't look into the phases. So yeah.
Okay. Luis, you are muted.
Thank you, Maximilian. Sorry. Meanwhile, I was muted. I think one question is coming. I think we have 1 minute to see. Probably is writing. Okay. Daniel Hodge says, thank you, Vincent. Did you consider twinning?
No. I only looked at intrinsic stocking, I1 stocking fault, so I didn't consider for the tuning. So there are other stocking fault differ as well, but as a consideration, so we already know the I1 stocking fault is related to the ductility. So we only consider the I1 intrinsic stocking fault for the current study. So because it's already related, so I think I answered the question.
Okay, thank you. Moving, just pay attention if any new question come in the Q8 chat. Let's thank again to you, talk. Thank you for the great job, Smovin. Let's move on to the next speaker, the last one from our symposium. Before to give into the board to Professor Maximilian Fechner, I would like to thank all the imaging partners, all the seniors at John Santi for the contribution made during the day. Really glad to see all the progress of the project. From my side, I would like to thank also to Daniel, Maximilian Group, Poly Cluster, and KIT for the support and let me also to show today our output so far achieved in the Imaging Consortium. Please, Alberto, if you had anything else to add?
Thank you, Luis. I want to thank again to Maximilian Fechner Group for the organization of this great international symposium in magnesium batteries. And I'm happy to view there are a huge and important advances in the field. It has been demonstrated in the presentation. I expect that the next year we will be able to see real and practical batteries based on magnesium batteries. Okay, Maximilian.
Yeah, thank you very much. Thank you very much, Luis, for guiding us through the entire day today, and also Alberto for organizing all this second day. Yeah, I mean, although the format was quite different that time, I think it was a fruitful event, and I hope you enjoyed it. At least I did. I learned a lot, and of course, I hope that in 2 years we will be able to meet us again face to face and really have these nice discussions. I was really missing you guys, because we have a fantastic day today in Ulm. The weather is sunny, and we have this river, the Danube, next to our actual meeting place, and across the river there is Oktoberfest starting on the Bavarian side. So what did we learn in this meeting? So yesterday we learned a lot about new materials for cathodes and electrolytes. There were several contributions which looked at details in the interaction of magnesium ions with solvent molecules. I think this is a new field that is coming up, and also the interaction of the electrolyte with the anode. Today, the results were presented from the European project IMAGIC, with modeling work of new candidates for insertion cathodes. It was an honor to have one of the originators of the whole field here, Doron Auerbach, who presented their results on electrolytes mainly. We saw results from cathodes, which were developed in or have been developed in IMAGIC, and also from pouch cell studies. So this is now coming up as our materials improve. There were new aspects brought up by ion pair studies, and polysulfide studies shed light on the magnesium-sulfur battery. There was an example of a vanadium sulfide-coated vanadium oxide system, and some suggestions for anode alloys, and also this new vanadium 6013 cathode material and how this can be magnesiated. So let me just conclude by expressing my sincere hope that we will meet each other again. And I would like to thank all the people who contributed to this event, or in particular our friends from IMAGIC. I would like to thank Daniel very much, who did a lot of work in contacting all the people, and also Christian Punkt, who did the managing of the event yesterday. And with that, I'm finished. Thank you again all for joining. Thank all the contributors, and let's meet us again in 2 years. Thank you very much.
Thank you very much, Maximilian.
Thank you very much, Maximilian, Daniel, hello everyone. See you next 2 years.
Bye-bye.
Bye-bye.
Bye.